We're using Revit as a drawing tool, as a modeling tool, but also as a communications tool. It enables us to work, I mean, ideally on one platform. We have the capability of doing that. We have projects where we're working on one platform, where we share a model, or we have individual bits that feed into one master model. But it isn't always the case, but it is enabling us to exchange information in a very efficient way. And I think the biggest step forward is that, I mean, we exchanged information with CAD drawings as well, but in the end, this is just lines. They don't carry any intelligence. And it's the big step forward is now that there's more attached, more data, more information attached to what we are drawing or what we're modeling. It isn't just geometry. And I think that's where that step happens. That when I talked about our workflow, initially it's about geometry, but then very quickly you move into giving that geometry or these individual elements that make that geometry some properties. And those properties can be material, or in our case, material or structural properties, but they can also have volumetric, mass properties, things of that kind. And that opens up a complete new world. We have, for example, developed our own carbon tracker, where we take the information that we get from our Revit model and link that with a carbon or embodied energy database. And we can evaluate how much embodied carbon equivalent or energy we use in our buildings. We've successfully did that recently with a project with British Land, who were very much tuned into this process. Very, very interesting. So all of a sudden it opens a new door where previously you would have a spreadsheet in hand counting things. You can actually have a tool that allows you also to measure these things as you design. So it's not just counting it all up in the end or having all the properties in the end. It's an evolving thing as you develop your design. The Glasgow Museum of Transport is a relatively small project, and the boundary conditions or the site conditions were not without their tricky bits, but actually not that tricky after all. But the building itself was highly complex geometry that needed to be translated into something that is buildable. And it's easy to draw something that has the zigzag shape of the roof of the Museum of Transport here, but translating that into in the first instance, a concept that is buildable effectively. What are the parts? What is the logic behind the parts that will make the building in the end? And ultimately translating that into information that allows us to build it from. That was rather interesting. And so again, we took several steps here. The first step was really, again, using a parametric model, a Rhino grasshopper model, to develop the geometry really just as lines to ensure that whatever we develop as a concept, the geometrical concept actually works just purely in setting our terms. The second step was then to develop this into a model that everybody can work to. A model that sets out the steel, that is basically the skeleton of the building, and a model that allows us to use all the spaces that we are creating in the most efficient way, in particular put all our building services in. Because what's most interesting about Glasgow Museum, you've probably seen the pictures, the steelwork is highly complex, and some people even asked why did we clad it, because it's so interesting and all that. It was never designed not to be clad, but it's a different story. But the more interesting thing is actually what you don't see, and that's all the building services. It's a museum, so we had to develop a building services strategy that allows it to be humidity controlled, temperature controlled, and so on. It is a museum. It has artifacts in there that need a stable environment. And one of the main reasons why Glasgow built a new museum was because in the old museum there was none of that. So you had old coaches rotting away and pieces of wooden artifacts that started cracking because of the changes in temperature and humidity. But Zaha's didn't want to see any of this, so it was not to be a building that was sort of designed around ductwork, So we had to hide all this, and we used the wall spaces to hide all the air supply. We have a rather elaborate system of super trenches, we call them. It's effectively walkable trenches under the building that take the air ducts from the central air handling plant and cooling plant into all the walls, where they then throw the air into the main space. And all this is absolutely invisible. If you go there, all you can see is a grill. But the spaces that we created with this building weren't necessarily the square spaces that you need to fit in an air handling unit. You know, they had these zigzag roofs and everything, different pitch angles and so on. And 3D modeling helped us immensely to actually utilize these spaces in the best possible way. And you know, I have pictures of that which we will look at, that show how we optimally used the space, fitted all the plant in, routed all the plant, and that was before we even built it, yeah, because again, building services very often that is then done by the contractor who actually provides these bits, but we had to do it in that way.